Hello everyone. If you like to share the event on social media, you can do that using the hashtag CodeGen2021 or the other below. I'm Daniel and I'm senior .NET developer on Microsoft Technologies. And in today's talk, I will show an interesting use case mixing deep learning and machine learning with ML.NET. Traditional programming is all about getting the input data, apply some rules, and in order to come up with an output. And this is the von Neumann architecture since 1945. We are so used to this that we don't even realize it. Okay, I will continue. I hope I'm ready to go. Now, take a look at these pictures. We are so proud of this. In the first picture, many people planning, processing, using their brain 8 hours per day to do their work. In the second picture, the evolution. Many developers planning, processing, using their brain 8 hours per day to do their work. In a way, we train people to be developers. Indeed, it is evolution, and it's here for 75 years now. We put our intelligence, the algorithms, in machine code, and that's pretty static. I will tell you why. On the other hand, let's bring some AI into the scene. In machine learning, data goes in as input, and the learners that learns rules that come out as output. Even more, the machine learning is live algorithm. Your code is not, because your code is not adapting itself. I agree, it runs on some predefined ranges, but it's not adapting. With every build, your code turns into stone-engraved binaries. So why not to rely on the machines to create the algorithms or intelligence? Now this is scary, right? Where are all the people in the second picture? Well, maybe having piña colada on the beach. Okay, I'm sorry guys, I'm kidding. We have COVID, remember? Now, let's get serious again. I have an interesting hypothesis for you. Has machine learning more human-like behavior than traditional coding? The answer is yes. And let me give you an example. Writing an algorithm is like writing a cooking recipe. Ingredients and the steps you have to follow are there. But you did the recipe before. The machine is only running it, right? Is the machine intelligent for running your recipe? Is this making the machine more human? Not really. On the other side, failing, succeeding, and repeating until the recipe is good, this is more human. This is what machine learning is doing, and this is similar or inspired by human intelligence. And this is making the machines more human than coding. We, as developers, have to be prepared for this new coding paradigm, I mean machine learning or AI, because in 10 or 20 years, it will change the way we code. Until then, we continue to write our own recipes. Look at the first picture. We have the machines, but we are still doing the hardest part here. Hundreds of millions of developers are writing cooking recipes, and the machines are just blindly running them. But this will change soon. In the talk today, I will show you how we can make a small step towards this change. In the world of data science and machine learning, Python programming language is making the rules. In addition to that, the existing frameworks like TensorFlow, Keras, Torch are not easy to integrate with .NET projects. I'm assuming you are a .NET developer. If you are at this talk, how many of you are happy to learn Python or other languages only to get some AI into your projects? The question is not to have or to not have machine learning framework. The question is, what is the best framework for you? As a .NET developer, of course, because you want to write some machine learning. Well, ML.NET is built upon .NET Core and .NET Standard, inheriting the ability to run on Linux, macOS, and Windows, of course. And it's designed as an extensible platform. Therefore, you can consume models created with other popular frameworks like Onyx or TensorFlow, CNTK. Microsoft ML.NET is more than machine learning because it includes deep learning and probabilistics, and you have access to a large variety of deep learning scenarios like image classification and image detection. When I first have to deal with machine learning, because I'm not a data scientist, I believed that finding the right trainer is the hardest part. Totally wrong. As a proof, very soon, AutomateML was released, which is able to detect which is the best trainer for a specific task only by measuring the model quality. The hardest part is to get everything ready for building the model. And that's preparing the data for your scenario. Let's state a few things. Your machine learning model cannot be better than your dataset, right? Even more, it's more important to have a good dataset than having the smartest algorithm. A bad dataset drives to a bad machine learning model. Keep that in mind. So be very careful when preparing the data because your data contains your biases. But what happens if your data is not good enough? If you decide to save some time skipping data preparation, do not be surprised if you have to pay the price later. You will waste a lot of time and not in a productive way. If it's something I would like you to get from this talk, this is that thing. Data preparation debt. Because it's similar to technical debt, I will call it data preparation debt. Now, about the data. An observation is a collection of lines consisting of features or readings. The supervised learning needs a special feature which serves as target feature or label. My use case used for this demo is supervised learning, or more specifically, it's multi-classification. Therefore, my label will be a category. Now, let me tell you about a real-world scenario. Let's suppose we have a system able to read temperature, luminosity, infrared radiation, the distance to source which is emitting these radiations or luminosity, and the creation daytime. And let's assume we have already a data set consisting of 1,000 observations. But how much data is enough? Well, this comes with experience, but keep in mind, you have more categories. If you have more categories or classes, you need more data. Or if you need more precision, you need more data. Too much data never hurts, as long if it's a good data, of course. Now, these observations are labeled, as I said before, and that means we have a feature named source for this readings for every observation in the dataset. Actually, the source from the sensors is generating these observations. And these sources can be a flashlight or a lighter or an infrared emitter or simply daylight. Let me exemplify. We have a dataset with a set of sensors reading from an IoT device, and we want to predict the source of these readings. For example, we have 20 Celsius degrees, 90% luminosity, zero infrared, 100 centimeters distance from the source, and it's created now. Well, most probably this is a flashlight because it's a cold energy, no temperature, not too much, yeah, but luminosity, no infrared. In the same time, if it's a lighter, we can sense infrared. Well, data from sensors can be calibrated or uncalibrated depending on the sensors. But let's think about something else. Let's think about, we have here 1, 2, 3, 4, 5, 6 columns, okay? But think about if we have a dozen or more. It becomes very soon incredibly hard to discriminate between the categories from so many analytical data. Our brain is simply not built to identify large-scale analytical data. Our brain seems to be much more adaptive for this. Even if there are involved more than 6 features for recognizing images, for example, our brain performs better because it's trained to recognize such objects. It's trained for an entire lifetime. Actually, our brain has its own model. And there is even a job for this. Lots of companies are offering image labeling services where people are labeling shapes in pictures all day long. But again, what about the analytical datasets? Who's labeling analytical datasets? There is an incredible hunger for data. I had some ideas where I could use machine learning before, but guess what? No data. Data is everything for machine learning. No data, no party. And no model can be trained with void data. Now let's see how we can label some data. Well, on this timeline, the past, it's the past. We cannot do much about it, but for the present and the future, we can do a lot if we have something with good eyes and good ears. I'm talking about what? About computer vision, of course. Yes, an IoT device has better eyes and better ears and much more senses, much more sense than the human have. We can train a deep learning model to recognize a small set of categories for our use case. So again, we can use deep learning to recognize the categories. And then we will use those categories to label our analytical data. This is our use case. And we have to do this one time. And indeed, we can expect to perform better than humans in the most of the tasks. The benefits? You name it. It doesn't get tired. It doesn't fail miserably because we tend to evaluate human skills at their best shape. But what about bad days or fatigue or stress? We are making mistakes. All this labeling system can be automatized and it needs none or very little human intervention. Well, bring the pina colada, baby. I said we cannot do much with the data in the past. Well, it's even better. For the near past, we can do something. We can do pre-labeling, which is not involving deep learning, but it deserves it to mention because it's a very good technique to get the data sets labeled. Let's discuss a little. If you are doing pre-labeling, we are presetting the system in a category mode, for example, a flashlight. And then we start gathering data. All the data will be labeled as flashlight. This is pre-labeling. We know in advance. Does not involve artificial intelligence. It's only a little human supervising, but you are staying drinking your pina colada until you are done, and then you are stopping acquiring data for that category. And then we do the same for another category. It's the cheapest, but at least, well, it's cheapest in terms of complexity. It's easy, but it still needs human intervention. Well, then it's smart labeling. I call it smart labeling because it needs AI and because it's real time. It replaces human completely, but it needs additional context. What's that? Well, let's think about a human. If it's a human instead of AI, the human needs to observe and to take decisions for labeling. It needs eyes and ears, right? Well, we do the same. We need the same from the computer vision. Then it's post-labeling. What's post-labeling? This is interesting as well because it's done post-factum. It's in the future. It's easy to do that, but we need to capture the context. It doesn't sound very appealing to register, to record a context like a movie or something, and by the timestamp to take decision in order to label your analytical datasets. But it's possible. It's a scenario where real time is not possible, and you are good to do that later on a more powerful machine, for example. Let's talk a lot about IoT. IoT will play a critical role for artificial general intelligence in the future. It is now already. We can use IoT devices with sensors and computer vision to replace humans in some areas of dataset labeling, as I said before. For my demo, I have used a Raspberry Pi and a set of sensors for luminosity, temperature, distance, or infrared. But we can imagine any scenario like another sensors or as many as you like. And we are expecting to identify 4 categories, and that's flashlight, lighter, infrared, and daylight. These are, okay, let's not get it too complex here. We just need to label this data with these categories. And then we will use deep learning to train our system to recognize these categories. On one side, machine learning uses algorithms to process data, to learn from the data and make informed decisions based on what has learned. On the other side, deep learning structures algorithms in layers to create an artificial neural network, and that can learn and make intelligent decisions on its own. They are both part of artificial intelligence, but deep learning is what powers the most human-like artificial intelligence today. Let's not ignore machine learning. What is TensorFlow? TensorFlow, of course, very probably you already know. It's very well known. This is maybe the most known library for artificial intelligence. It's an open source developed by Google, but it has support for Python, Java, C++, but you know what? It has support for C# as well. It's ML.NET is not yet supporting it for training. We can only infer or consume the models, but there is another library which can do that, and it's TensorFlow.NET SDK. So we can use this in addition to ML.NET to be completely independent from other platforms and yet to do TensorFlow models. So as I said, currently ML.NET is limited to inference and transfer learning. I forgot to tell you, and transfer learning. It's very important because we will use that. Well, nevertheless, training a deep learning model can take days or weeks. And nevertheless, it needs very powerful machines. For example, you can do inference on images using the TensorFlow inception model. I will tell you a few things about inception in a bit. And this model is used for image classification, and it was pre-trained with millions of images like animals, vegetables, or other things you can find in your day-to-day life. Inception is a convolutional neural network, and it can load a pre-trained version. We can load actually a pre-trained version and use it as it is. It will detect one image in these 1000 categories. It was trained to detect objects in 1000 categories. We have 1000 labels there, but we can reuse it and train it for our own sets. For our use case, it's 4 categories. How we do that? We will use transfer learning. Transfer learning is a machine learning method where a model developed for a task is reused as the starting point for another task. So we don't have to do all the training. But why would do this transfer learning? Many times you don't want to limit the predictions to the existing classes. We need to predict for other classes which you don't have. Well, to do that, you might want to intercept the final layer in this set of layers from the model and complete the training yourself with your own set of images for your desired classes or categories. Because Inception has already the muscles to do the recognition. It knows about small shapes, about lines or edges or corners, shadows, and it knows about larger shapes like a leaf, a nose, I don't know, a wheel. And we need these muscles to train it with our own objects, like specifically a lighter, a flashlight, maybe a match, a torch, a finger, a hand, whatever it can get into the front of the camera, and whatever we decide to train for, right? Let's take a look at the far right end in the picture, the blue dot. Well, that's the classification part. So below we can see it scale it up. It's easy to identify, and we don't need to understand all the process, how it is done, but let me exemplify a little. So we have in the lower part softmax pre-activation layer. This is the layer where we can stop if we want to do transfer learning. After this, there are a few more layers, right? But we don't need them. So we will instruct our model to stop before the red area, because we plan to train ourselves that part in order to make our system able to recognize our categories. Now, the coding part. You can see in the first line of the code a method. It's load from enumerable, but it's called with an empty list of objects. How is that? Since we plan to do only scoring, we don't need to load input data when building and training the pipeline. The muscles are already there. Right? But we still need this for reading. We still need to create an empty list because we need to read the data schema. That's why. Next, a training pipeline is built with an image and models loaders and a few transformations like resize image or extract pixels. And then the score TensorFlow model is meant to prepare the image for scoring. But how do we realize the transfer learning by code? Well, as I said, the pipeline is stopping at layer softmax 2 pre-activation, and the rest is ignored. In addition, we have to take care ourselves or multi-classification because we have our own classes now. Let's see it side by side. So in the left part, this is our model. In the left part, we have data because we have our own images, which we will use to train the model. In the right part, we don't have data sets because it's already trained. We are just in the right part, we are just consuming the model, but it will predict the standard 1000 images categories, which the model already know. So, as you can see, the gray part, we have to provide ourselves some trainer to do the classification for our categories. But that's it. It's not complicated. It's only a few lines of code will do what we need. Let me show a little demo. Okay, this demo, it's pre-recorded because it's very hard to talk and to manipulate my keyboard and in the same time to manipulate the system. So it was pre-recorded. But I will explain it. Now the real-time labeling in the recording is live, and now the data is sent from the sensors to the desktop application for labeling. The camera capture is sent as well to the desktop application. Now we have the readings, and by extracting the label from the image, we can label real-time the readings. Daylight is the default mode, therefore all readings which are not identified to be part of some other categories like light or flashlight, it's assumed as default to be daylight. But now let's set up the lighter mode. As we can see, the lighter is detected and recognized. Another important thing here is we can choose which data to keep in the dataset. In that way, we can prevent bad data caused by manipulation of the system. Now let's see the flashlight. We can read more datasets until we have enough data from each category, lighter, flashlight, infrared, and we can save these categories as CSV files. And this is what we want, to produce datasets which are already labeled. So we use deep learning for identifying the source from the sensors and to automatically label our analytical data. We save a lot of time doing that because we only have to start and stop the process and choose which data is better for us. Okay. We can see some data are detected as bad data by the system. So it's automatically suggested for not keeping it. But we can do manually this selection. Of course, this can be improved in order to help us to do that faster and more efficient, but it's only a proof of concept. And this is the real-time labeling, what I presented. We can do pretty much the same for post-labeling, but we have to keep the recording from the webcam. We have to keep this is a set of information. Then we can keep the readings from the sensors and process the image later in order to label our data set. And let me show you the pre-labeling. For pre-labeling, we are presetting the mode, what we are reading, for example. It's not using deep learning, as I said before, but it's very useful to produce data. So we first select the source and we start reading the data. All data are labeled with the preset label, of course. For example, we had it there, the flashlight. Okay, now we have enough data produced in one of these ways. And now we can go to check how good is our data. And for that, we will train a multi-classification model with our data and check the quality of the model. And for that, we can select which data sets are good for us. Maybe a good name would be here the daytime. These are the ticks from the daytime. It's not easy to understand, of course, but we can use hour, seconds, day. So having this data, we can train our model with these data sets. Let's remember I have acquired only little data here, but still the accuracy is very good for so little data. 70 some is not bad at all if we consider the small number of the lines of the readings. For example, we have here in total a few hundreds. With enough data, maybe a few thousand for each category, the accuracy is close to 100. So it seems to perform better than humans, and it's consuming only power. It's not failing miserably because human mistakes. It only needs to be adapted for specific use case. Actually, I think this is the hardest part to prepare the IoT environment to replace the human. But comparing the costs, definitely it's an advantage. Okay, now some takeaways from this demo. This demo was an idea how we can integrate easily Microsoft ML.NET in our projects and how we can mix deep learning and machine learning to benefit from the power of both. Let me show you a little the code because we are all .NET developers. I assume I have built this with .NET 5, no problem with that. And I have 3-4 projects here. Is the API which runs on the desktop. Then it's a smart labeling camera which runs on an IoT device which is capturing the images. Then it's smart labeling.ml, which is another project which runs on another Raspberry Pi, which gets the data from sensors. So we have a few IoT devices. We can have more devices. For example, we can have more camera devices to capture the context from different angles. Of course, it can be improved, and but the results are very good. Let me go back to the presentation. Let me tell you about some takeaways. So ML.NET, it's not going to replace existing frameworks like TensorFlow or Keras, but considering the AI is going to be adopted by the majority of the applications, as a .NET developer and not having a data science background as me, I prefer a code-first framework. ML.NET is very easy to learn, and you can use it on-premise. You can use it on-premise. You can build applications and run it on different platforms. Soon, ARM CPUs will be supported too, I was told. But for now, I've tried something interesting. I have put it in Blazor, deploying it on a Raspberry Pi, and run some machine learning from Raspberry Pi. Of course, it's not per se running in the Raspberry Pi process. Only the code is there, but I'm loading the Blazor page, and the inference is done in the browser. But what's nice here, we don't have to keep anything on external machines. We can keep everything on Raspberry Pi and then use a browser and do the inference, the predictions. Why we cannot do training on Raspberry Pi, not on Raspberry Pi, on Blazor yet? It's because the JavaScript limitations related to single-threaded processes. Only inference is supported for now. I think in order to make machine learning supported by Blazor entirely, the code should be forced to run single thread. And that's not a good idea in terms of performance, of course. But for now, this is supported, inference. So you can build the machine learning on other platforms and consume it in Blazor WebAssembly. But this is good enough because usually we don't expect to train a model in the browser of an IoT, right? Or on an IoT or in the browser. But we still want to consume. Well, this is the topic for today. I'm available for questions, and I will wait for the questions, of course. I will stay live for the next, I don't know, 5 minutes or more. And okay, I have a question. Yeah, the sample is on GitHub. Actually, the proof of concept which I have used for this presentation, it won third place on virtualml.net hackathon 3 months ago. And the source code, it's on my repository, but it's on virtualml.net repository as well. So if you search for my GitHub profile, you will find it there. The name it's Apex, I guess it's apex.smartlabeling. This is a project which can be developed further, but of course I need more motivation for doing that, but as a concept it works. Thank you very much for being here today. I will still wait for new questions. I will leave this question for the future. Who's writing your recipes? I think I know the response now, but I'm curious about the next 10 or 20 years. Okay, let me respond to the QA question in Teams. Very welcome. Okay, thank you very much for being here today with me, and see you next time. Thank you for the organizers, and let's enjoy the rest of the event. Thank you. Bye.